Hello again. In the last two lectures, we discussed about paramagnetism and diamagnetism. Now, in this lecture, we are going to ask questions. What is the field of a magnetized object? So, what do you mean by that? I mean, you imagine a magnetized material with some dipole moment point volume A, which I have already defined this quantity. So, given you have already a magnetized material, the question is, what kind of field does it produce? To know that, we should first recognize the fact that the vector potential of a magnetic dipole is given by this expression, mu 0 by 4 pi m cross r cap by r square. Earlier, okay. But in this case, we have a volume element and we are having a magnetization point volume as m. So naturally, the dipole moment for this volume element will be this multiplied by the volume, and so this will be m d tau prime. So that is my dipole moment. Okay, m d tau prime for the dipole moment of this unit and the volume element. So now, if you want to calculate the total vector potential for this material, you need to integrate over many such volume elements, right? So then you write the integration m r prime. I mean, again, as we have already adopted the convention, the source is at you refer the source in the prime coordinate system, right? So there will be m r prime cross r cap by r square d tau prime. That's your integration. I hope you understand here. So now our job boils down to integrating this particular integral, right? So how do you calculate that? So you take the help of some vector identity. So you know your del prime 1 over r is r cap by r square. This you should verify again. I think you have already done one exercise for that. So once you now replace that, this is your r cap by r square, and you replace that with del prime 1 over r. So now your cross product becomes m r prime cross del prime 1 over r. Now you apply the product rule. So the product rule of del cross a scalar and a vector. So you have a scalar f, vector v. When you take curl of that, then your product rule tells that del cross fv is nothing but f del cross v. Sorry, this is v here, and minus v cross del f. So here v is a vector, f is a scalar. So if you apply that rule, you will have this. Now check it again, and once you now what you can do, you can convert the second integral in terms of surface integral. Okay. So if you do that, so your del cross m r prime over r d tau prime now becomes 1 over r m r prime dA cross dA prime. Okay, that's the conversion of volume integral into surface integral. Okay, why did I do that? That's because of the fact that you already know the definition of the vector potential in terms of your volume currents and surface currents. So let me remind you. So that's your definition of vector potential in terms of volume current, Jr, and surface current, Kr. Now what you do, when you compare now this expression, so you look, everything is same, besides the fact that there is a del prime cross mr prime in place of Jr prime, and there is mr prime cross dA prime in place of Kr prime. Okay, so we can rewrite it. I mean, now we have some sort of a volume current here and some sort of a surface current here. So now we can rewrite this vector potential in terms of just comparing the JB, some volume current JB by R d tau prime mu 0 by 4 pi, then surface integral KV R prime over curly R dr prime. Where JB now is your now nothing but del cross M, and KB is nothing but M cross N cap. Okay, so the dA prime here is no more a vector now, so you just remove the vector sign and the surface the normal is now N cap, so your M cross N cap will effectively gives you this with this cross product. Okay, this cross product. Okay, so now we have two quantities. One is JB and KB, which we now call as bound currents, bound volume currents, which is your JB, bound surface current, which is your KB. So what it means is that if you have a magnetized material, the field due to this magnetized material is effectively a field produced by a bound current JB, which goes like del cross M, and a surface current KB, which goes as M cross N cap. Okay. So the field produced by a magnetized object is the same as it would have been produced by a volume current JB and a surface current KB with these expressions. Okay, that's very important to recognize. But what are these bound currents? So in order to understand that, so we first recognize the fact that, so now let us analyze the material. So think of or take a slab of this magnetized material with thickness T. Okay, that's a slab of a magnetized material with thickness T. Now, as I have already told you, this material consists of many such tiny current loops, right? So now if you take two such adjacent loops, if you see that because of the direction of the current, so the adjacent sides cancel, and that will happen throughout this inside. Only where it will not be able to cancel is at the edges. Okay, because there are no adjacent loop to cancel this, so only at the edges this will not be cancelled. So what it means is that, so each dipole has a dipole moment perpendicular to this slab. And so if imagine if there's a current flowing in this each loop as I, so all the internal I will cancel. And so what remains is a ribbon of ribbon where a current I is flowing. Okay. So those tiny current loops inside is now appearing as if there is a current I flowing at the boundary, okay, in this ribbon. Now, what is this current? So now imagine take one such loop now. So if the thickness is T, what should be the magnetic dipole moment for one loop? So let me write it now. Your magnetic dipole moment M, I'll write the small m. So the magnitude is nothing but the dipole moment per unit volume, that is your capital M multiplied by the volume. And so the volume is your area. So let's say the area is A and thickness. Okay, so that's your magnetic dipole moment for each loop. Okay. But there is a current I circulating in this loop. So which means in terms of current, I can write same M as I multiplied by A, the current into area, right? That's very simple. So which means you can compare these two and then you can write that I is nothing but capital M T. Okay. T is your thickness. So what in terms of surface current, what happens? So your surface current, the magnitude of the surface current KB will be I, the current divided by the perpendicular length, right? So which will be I divided by, so the current is flowing like that and the perpendicular length is T. If you remember the old lectures where I have shown you, if there is a V1 current flowing, so like that, and then this is your some D, then your if there is a I current flowing here, so your I by D is nothing but K. So here I by D is nothing but surface current. So similarly here, your I by T will give you KB, and that is nothing but, if you look at I by T, that is nothing but M. Okay. And what should be the direction? Now the direction will be given by, as you can see from this particular picture here. So your M is along this direction, N cap is pointing towards surface normal of this. So the direction of KB will be now given by, so KB direction now will be, the direction will be picked up by the cross product of M cross N cap. This you can be easily verified from here. So that's your M, that's your N. So the cross product will give you the direction of the KB. Okay. So now I hope it's clear. So effectively what we have done is that the tiny current loops inside gives rise to a surface current at the boundary. So there is I mean the interesting thing is that no single charge, there is no you don't have a charge which is kind of going along this and completing the whole journey. Okay, because the charges are going along these loops, they are still bound at the site of the atom, right? These loops. So you don't have any charge which is completing this loop, but still you have a current there. Okay, so that's actually why we can call it a bound current, because the charges are still bound. Okay, each charge is moving only in the tiny loop in the single atom. However, the effect is very macroscopic, and the effect what we get is a surface current flowing along the boundary. Okay, that's the whole idea about the surface, the bound surface current KB. Okay. Now, what about the volume current, bound volume current? Okay, for that, so if you consider a non-uniform magnetization, so what happens? So if you have a non-uniform magnetization, what does it mean? So it means that the magnetic dipole moment for each loop will be different. Okay, so for example, this one will have M1, this one will have M2, and your M1 can be greater than M2, or M1 can be smaller than M2. Okay, so that's what essentially means by the non-uniform magnetization. Now, if that happens, what does this inside loop cancels out then? No, right? So now we can effectively analyze it using at least in one direction. What we can see. So now, since you have a non-uniform magnetization, so your internal currents now will not cancel. Okay. So if you consider now two adjacent such current loops, okay, again we have a thickness Tz, and then you have two adjacent current loops where you have MZY. So you are having a separation here as dy between these two loops, dy. Okay. So the two adjacent loops placed at a distance dy. Now for this loop, you have a magnetization which is your MZY. For this loop, of course, it will be MZY plus dy, because now you are not having the same magnetization everywhere. Okay, so now if mz y plus dy is greater, I mean, as it is drawn in this figure, the arrow is greater now here. So which means this is a mz is greater than mzy plus dy. So this magnetization is greater, and that means that the current flowing here is greater than the current flowing here. Now, if you look at these two sides, this side and this side, so the current goes like that, and here the current comes like that. Earlier case, when the magnetization was uniform, they used to cancel. But however, this is no longer the case. So the current will not cancel. So the current will have a net component along this axis, right? Along this axis, along x direction. So which means now you can write your current, net current Ix will be nothing but your mz, your, because your magnetization is along z direction. So y plus dy minus mz y, and that multiplied by dz. Okay, this is nothing but we are using this expression, right? I equal to mt, magnetization into multiplied by the thickness. So here there is a net current, so the magnetization, net magnetization multiplied by the thickness. Now this expression, if you I am sure you know this, that this is nothing but the derivative. So this effectively we can write this del mz by del y dy dz. Okay, this I think I'm sure there is no problem in understanding how this expression gives rise to this one. Now, what is the now volume current density here? Now, if you think of JB along x direction, so that should be now Ix divided by the perpendicular, the cross-sectional area, and the area is nothing but dy dz. So the area is dy dz. So you have to divide that to get the JB, the volume current density, and that is nothing but del mz by del y. And you can do a very similar analysis for imagine you have a non-uniform magnetization along y direction now. So here the non-uniform magnetization is along z direction, and then you have a non-uniform magnetization along y direction. So for that reason, you will have another another contribution to this JBX, and that will be nothing but your minus del my by del z. So effectively now, so if there is a non-uniform if there is a non-uniformity along the y direction, so effectively your JBX will be del mz by del y minus del my by del z. So this is because of the non-uniform magnetization along z direction. This is non-uniform magnetization along y direction. So both the components will give you del mz by del y minus del mz y by del z. So just by looking at that, you can write a more common notation that this is only the x component. So similarly, you can get the JBY component and JBZ component. And what you will find that in general, you can write JB nothing but del cross M, because this is a component of the cross products. Okay. Okay, that's precisely what we got as the volume current, volume bound currents, bound volume currents. So effectively what it means is that if you have a uniform magnetization, your JB is 0. Okay. So for uniform magnetization, you don't have a bound volume current. So because of the non-uniformity in the magnetization, you have a bound volume current, which is nothing but the cross curl of the magnetic moment. Okay. So now let me take a very small example of this to demonstrate this magnetization. So the example, let me just take a very small example and show you how you can calculate the field when you have given a magnetization. So again, this is a problem, unsolved problem from the Griffith. So let's now what is given. Let me just see what is in my note. 1 minute. Yeah. So what we have here, the problem which there are two problems. Okay, let me solve this one, which is very simple and easy to solve. So we have a cylinder. So there is a example. So we have a cylinder. Okay. Okay. So you have a circular cylinder which actually carries a uniform magnetization. So you have a uniform magnetization M parallel to its axis. That is given. So you have given a M here. Okay, that's given. Now what it asks you is to calculate the magnetic field. So B due to M inside and outside. Okay, solution. So the solution, first let us look at the thing that the M is uniform. So there's a uniform magnetization M. So what it means is that your JB, which is your curl of M, so that becomes 0 because your M is uniform. And your KB, because see, if you are going to calculate the field, so the field will be field of a magnetized object is nothing but that what you would have got using a bound volume current and bound surface current. And in terms of magnetization, bound volume current is given by del cross M, and bound surface current is given by M cross N cap. Now here N cap actually will point like that, right? So that means M cross N should be your a component along phi cap, right? So it will be like magnitude M phi cap. Yeah. Yeah, please verify this, whatever I'm saying. Now, once you have that, what you have effectively, so you have a current along the phi cap, right? So like that. Now, if that is the case, you have effectively, it's like a solenoid. So this is now a solenoid. Okay, let me write that. So this is now a solenoid. And you already know the field due to the solenoid. So the field outside is 0. You please see the solenoid problem. Okay, the field outside is 0. The moment you know it's a solenoid, so you have a current which is along phi cap, so which means you can right away say that the field outside is 0. And what about field inside? So field inside again for a solenoid turns out that the magnitude of the field nothing but mu0 and the current kV, and that is nothing but mu0 m. Okay, and the direction is along same m. So the direction, if I want to put a vector there, so your B is mu0 m. That is your inside, that is your outside. Okay, so that's a very simple example to show you how given magnetization, how you can calculate the field due to the magnetization. Maybe we can take up one or two problems in the discussion class regarding this, and so that will kind of complete the discussion regarding the field of a magnetized object. In the next lecture, we will discuss about the auxiliary field H and the ferromagnetism. Okay.